Hello students, welcome back. Let us resume our discussion in section 3, related rates. We went through a couple of problems on 3D geometry, snowball melting, and then circular cone. How about the next problem here? 2D geometry, so this may be a bit easier. How about a picture here? Okay. A man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path. Yes, 20 feet from the path. And is kept focused upon the man. At what rate is the searchlight rotating when the man is 15 feet away from the point of the path? So x value is 15. So according to this, that's given. And then the distance, and then the man walking is the same direction. That rate of change is 4 feet per second. These two are given information. So that one we know, and then that we know. What do you want to find out? At what rate the searchlight is rotating? Theta. The rate of change for theta, that's what we're looking for. We don't know this. We don't know this one either. This one is the answer that I'm looking for. And this one may be necessary as an intermediate step. In any case, here's a setup. Now, what's the relation between the two? Relation between x and theta. Do you see that from this picture? We have a right triangle. We have theta. We have 20 and x. Nothing about hypotenuse. So this relation is, what is this relation? Sine, cosine, or tangent. Which is it? It's tangent. Tangent is x over 20, or equivalently speaking, x is 20 tangent of theta. That's how they're related. X is 20 tangent of theta, and then taking the implicit differentiation, what do you get? X prime is 20, and then the derivative, secant squared theta, and theta prime always pops up. So this is a quantity I'm looking for. And then that, I don't know. This one, I know. X, that I know that too. Okay, all right, let's go ahead and solve it. Currently 20, distance is x is 15, not 20. 20 is this one. This is 15. So 15 is 20 tangent of theta. Okay, all right. I can find tangent. And then taking out tangent, I can find out theta. All right. Now x prime is 4. And then secant squared. Okay, all right. If you know tangent, then I can always find a secant squared. And theta prime is the quantity I'm looking for. Okay, let's go ahead and find this out. Okay, all right. I can solve for theta by taking, 15 over 20 and then taking out tangent. But I don't think that's necessary. Secant squared is 1 plus tangent squared. Remember this? Pythagorean identity. So this 1 plus tangent is 15 over 20. That thing squared. So what is this? 225 over 400. So this thing is 625 over 400. Okay, all right, that's secant squared. So theta prime is 4 over 20 secant squared. So 4 over 20 and 625 over 400. And I've reached the point I need a calculator here. We have 16 over 125. That's a radian. So if you multiply 180 over pi, I'm going to get the degree. So 7.33 something per minute, per second, per second. Looks like I can answer like this. Or you can answer, of course, 16 over 125, or the decimal expression of it in radians per second. (16 over 125, 0.128 radians per second, or 7.334 degrees per second. Yeah, the same computation as we did. So we have this geometry, this right triangle here. So we have tangent of theta is x over 20. That's a relation. And then taking the rates, we get the second equation. The rates are related like this. So that's a related rate equation. And then x is 15, x prime is 4. Problem gave you that. Theta unknown, theta prime unknown. We don't really have to find out theta because what we need is secant squared of theta. So from tangent, I use Pythagorean to find out the secant squared. But of course, you can do alternative methods to find out secant squared as well, including finding out theta directly from here using arctangent expression and using calculator. All right, we went through some related rates problems here. None of them is straightforward, actually. All the related rates problems are there. And I typically give some project problems on optimization and related rates because they resemble the real-life application as much as we can see in Calculus 1. And they're both hard, but it's by short margin, but students struggle a little bit more in related rates compared with optimization. That was my traditional experience on projects on Calculus 1. We have one more topic to go, linear approximation. That's a review, and yeah, even though if it is review, I don't think I have enough time to cover that. So let's stop here and let's meet again for section 4 in a separate video.